Welcome. Tonight, we journey back to a time that lives vividly, yet often inaccurately, in our collective imagination. An age of immense ice sheets, colossal beasts, and landscapes sculpted by a profound and enduring cold. We travel to the Ice Age. But what comes to mind when you hear those words? Perhaps endless plains of snow and ice stretching to the horizon, woolly mammoths lumbering through a perpetual blizzard, saber-toothed cats battling giant sloths. These images, powerful as they are, capture only a fraction of the story, perhaps even a misleading one. The reality of the Ice Age was far more complex, more dynamic, and in many ways far stranger than the simple picture often painted. Tonight, we delve beyond the clichés. We seek to understand what the Earth was truly like during this most recent chapter of deep cold, the Pleistocene epoch. We will explore the sheer, breathtaking scale of the continental ice sheets, but also the vast, ice-free worlds that existed alongside them. We will listen to the sounds of its long nights, feel the bite of its air, and glimpse the lost landscapes now hidden beneath the waves. We will meet its giant inhabitants, yes, but also consider the subtle, pervasive ways this era shaped the very ground beneath our feet today. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here, and let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who is joining us, warm and safe, from around the world. Now, dim the lights. Maybe turn on a fan for that soft background hum, perhaps the sound of wind across a vast frozen steppe. And let's ease into tonight's journey together. Let's step back into the shadow of the ice. The term Ice Age itself invites a certain image, a single monolithic period of unrelenting cold. But the Earth's climate is a restless beast operating in long, slow cycles. The time we call the Ice Age was not one continuous deep freeze, but a dramatic series of glacial cycles, pulses of intense cold, where ice sheets advanced, separated by warmer interglacial periods, like the one we are living in right now, where the ice retreated. Our focus tonight is on the last great pulse of this cycle, the peak of the most recent glaciation, a time stretching roughly from 115,000 years ago down to about 11,700 years ago. This was a world profoundly different from our own, yet hauntingly familiar in its geography. The continents stood largely where they are today, but vast portions of them lay buried, asleep, under a weight of ice almost too immense to comprehend. It was a world held captive, sculpted and defined by the sheer, overwhelming power of frozen water, and its influence reached far beyond the edges of the ice itself. The very phrase, the Ice Age, plants a simple, dramatic image in our minds, a singular, epic winter that gripped the planet. We picture mammoths forever trudging through snow, glaciers perpetually frozen in place. But the Earth's climate history is rarely so straightforward. The reality of the Pleistocene epoch, the time we colloquially call the Ice Age, was far more dynamic, a slow, rhythmic breathing of cold and warmth, driven by the subtle celestial mechanics of our planet's journey through space. This was not one single ice age. It was a series of them, an alternating pattern of long, intensely cold glacial periods, where vast ice sheets grew and advanced, punctuated by shorter, warmer interglacial periods, like the one we currently inhabit, where the ice retreated towards the poles. This entire epoch, spanning the last 2.5 million years, was characterized by this constant ebb and flow, this planetary pulse. What drove this grand climatic rhythm? The answer lies not within the Earth itself, but far out in space, in the intricate clockwork dance between our planet and the Sun. These are the Milankovitch cycles, named after the Serbian mathematician Milutin Milankovic, who first calculated their profound influence in the early 20th century. Think of the Earth's orbit around the Sun. It is not a perfect, unchanging circle. Over vast stretches of time, subtle gravitational nudges from Jupiter and Saturn cause three key aspects of our planet's journey to slowly, predictably wobble and shift. First, the shape of Earth's orbit, its eccentricity, changes. It cycles from being nearly circular to slightly more elliptical, like a stretched-out oval, over a period of about 100,000 years. A more elliptical orbit means the Earth spends slightly more time further away from the Sun during parts of the year, potentially leading to cooler overall conditions. Second, the tilt of Earth's axis, its obliquity, rocks back and forth like a spinning top losing its balance. The tilt varies between about 22.1 and 24.5 degrees over a cycle of roughly 41,000 years. A greater tilt means more extreme seasons, hotter summers and colder winters. A lesser tilt means milder seasons. Third, the Earth wobbles on its axis, like that same spinning top, tracing a slow circle in the sky. This is called precession, and it changes the timing of the seasons relative to Earth's closest approach to the Sun, operating on cycles of about 19,000 and 23,000 years. These three celestial rhythms, the stretch of the orbit, the tilt of the axis, and the wobble, overlap and interfere with each other in complex ways. They don't dramatically change the total amount of sunlight reaching the Earth, but they subtly redistribute where and when that sunlight falls, particularly impacting the intensity of summer sunlight in the Northern Hemisphere. And this, it turns out, is the crucial trigger. If Northern Hemisphere summers become just slightly cooler due to a particular alignment of these cycles, the snow that falls during the winter doesn't completely melt away in the summer. Year after year, the snow accumulates, compressing under its own weight, transforming into glacial ice. Reflecting more sunlight, cooling the region further, allowing more snow to accumulate, the ice albedo feedback loop kicks in. A glacial period begins. Then, as the cycles shift again, as Northern Hemisphere summers gradually become warmer, the balance tips back. Melting begins to outpace snowfall. The great ice sheets pause, hesitate, and then begin their long, slow retreat. An interglacial period dawns. This cosmic metronome, these overlapping Milankovitch cycles, set the underlying tempo for the Pleistocene Ice Age. It wasn't a constant winter, it was a slow, celestial waltz between ice and warmth playing out over hundreds of thousands of years. Our focus tonight is on the last great glacial advance within this long epoch, the peak cold of the most recent glacial period. But understanding this cyclical nature is key. The world we are about to explore was not static. It was one phase, albeit a dramatic one, in an ongoing planetary rhythm dictated by the subtle mechanics of the heavens. The Milankovitch cycles had aligned. The subtle dimming of northern summers had tipped the planet's climate over the edge. Snowfall began to outpace melting, and over tens of thousands of years, accumulating layer upon patient layer, two colossal entities were born, geological monsters that would define the very character of the last glacial maximum. These were the great continental ice sheets. We must erase from our minds the image of a mountain glacier, a river of ice flowing down a valley. These were something else entirely, operating on a scale that beggars the imagination. These were ice sheets that covered entire continents. In North America, the Laurentide ice sheet grew to become a behemoth of almost inconceivable proportions. Centered roughly over Hudson Bay, it spread relentlessly outwards, eventually burying almost all of Canada and extending deep into the northern United States. New York City, Chicago, Seattle. The future locations of these great metropolises lay entombed beneath thousands of feet of ice. At its peak, the Laurentide sheet covered over 5 million square miles, an area larger than the continental United States today. And it was not just vast, it was thick. Over its center, the ice accumulated to depths of perhaps 2 miles, or over 3 kilometers. Imagine 2 miles of solid, compressed ice resting upon the land. The sheer weight was astronomical. Across the Atlantic, a similar, though slightly smaller, giant was forming. The Fennoscandian ice sheet. Centered over the mountains of Scandinavia, it spread outwards to cover modern-day Norway, Sweden, Finland, engulfing the Baltic Sea, burying Ireland and most of Great Britain, and extending across northern Germany and Poland, reaching deep into Russia. It too reached thicknesses of perhaps over 1.5 miles in its central regions. These were not static blocks of ice. They were living, moving entities, albeit on a geological timescale. Under their own immense weight, the ice deep within the sheets behaved like a slow-moving, incredibly viscous fluid. It flowed outwards from the centers of accumulation, grinding inexorably across the underlying bedrock. Imagine the power of this slow-motion advance. Hills were rounded off. Valleys were deepened and scoured into characteristic U-shapes. Mountains were carved into sharp peaks and arêtes. The ice acted like planetary-scale sandpaper, scraping away soil, plucking boulders the size of houses from the bedrock, and carrying this immense load of debris frozen within its body for hundreds, even thousands of miles. The edges of these ice sheets were dynamic zones. Great lobes of ice would advance and retreat slightly with minor climate fluctuations. Where the ice met the ocean, immense cliffs of ice, perhaps hundreds of feet high, would have loomed over the frigid water. Huge sections would periodically break off with thunderous roars, carving massive icebergs that would drift southwards into the colder, lower oceans of the time. To stand near the edge of one of these ice sheets would have been to stand in a world utterly dominated by ice. The air would have been intensely cold, blasted by katabatic winds, dense, frigid air flowing down off the immense ice dome. The sky might have been perpetually grey, heavy with moisture evaporating from the ice surface. And the soundscape would have been one of groaning, cracking, and the distant deep rumble of the ice itself, moving, shifting, alive with its own immense, slow power. These two great ice monsters, Laurentide and Fennoscandian, along with smaller but still significant ice sheets covering Greenland, Antarctica, which was even larger than today, and mountain ranges across the globe, were the defining features of the glacial maximum. They were colossal reservoirs of frozen water, locking away so much of the planet's H2O that global sea levels plummeted, and their sheer physical presence exerted a force that reached far beyond their icy margins, pressing down on the very crust of the Earth itself. These colossal ice sheets, Laurentide and Fennoscandian, were more than just immense blankets of frozen water draped across the continents. They possessed weight, a staggering, almost incomprehensible weight, born from miles of accumulated, compressed snow and ice. And this immense burden did not rest lightly upon the land. It pressed down with a force so profound that it literally dented the planet's crust. We think of the Earth's crust, the solid rock beneath our feet, as rigid, unyielding. But on geological timescales and under sufficient pressure, it behaves more like an incredibly thick, slow-moving fluid. It rests upon the softer, partially molten layer beneath it, the mantle, in a state of buoyant equilibrium, much like blocks of wood floating in water. This is the principle of isostasy. Now imagine placing an object weighing trillions upon trillions of tons, the weight of a continental ice sheet, onto one of these floating crustal blocks. The equilibrium is disturbed. Slowly, patiently, over thousands of years, the crust beneath the thickest part of the ice sheet begins to sink, pushed downwards into the yielding mantle below. This process is called isostatic depression. The land beneath the Laurentide and Fennoscandian ice sheets subsided significantly. The very rock foundations of North America and Northern Europe buckled downwards under the immense load. Estimates suggest that the crust beneath the center of the Laurentide sheet may have been depressed by as much as half a mile or nearly a kilometer. Think about that. The land itself, the solid earth, sagged under the weight of the ice, creating a vast, shallow bowl in the continent's surface. This depression had subtle but significant effects even while the ice was present, influencing the direction of meltwater flow beneath the glaciers, and perhaps even affecting patterns of volcanic activity near the ice margins. But the true dramatic consequence of this Great Depression would only become apparent after the ice was gone. As the climate warmed at the end of the last glacial period, as the great ice sheets began to melt and retreat, that immense weight was slowly, painstakingly lifted, and the Earth's crust, like a colossal slow-motion memory foam mattress, began to rebound. Freed from its icy burden, the land started to rise again, seeking to return to its original state of buoyant equilibrium. But this process, isostatic rebound, is incredibly slow. The mantle beneath the crust flows like incredibly thick honey, resisting the upward movement. And astonishingly, this process is still happening today. Large parts of North America, particularly around Hudson Bay, which was near the center of the Laurentide ice sheet, and Scandinavia, the heartland of the Fennoscandian sheet, are still slowly, measurably rising, tens of thousands of years after the ice disappeared. In some areas, the land is rising by as much as a centimeter or more per year. Ancient coastlines, beaches formed just after the ice melted, can now be found miles inland and hundreds of feet above current sea level, lifted skywards by this slow geological sigh of relief. This ongoing rebound is perhaps the most tangible, most profound physical legacy of the great ice sheets. It is the Earth itself, still adjusting, still remembering the colossal weight it carried during the last glacial maximum. The ice crushed the land, depressing it by hundreds of meters, and the land remembers. Its slow, patient rise is a silent testament to the sheer, planet-altering scale of those forgotten ice monsters. It reminds us that the Ice Age was not just a surface phenomenon. It was an event that exerted a force deep into the very substance of the Earth, a force whose echoes are still shaping our world today. And the influence of that ice reached far beyond the land it directly covered. The colossal ice sheets, Laurentide and Fennoscandian, dominated the northern continents, vast frozen deserts seemingly devoid of life. But it is crucial to remember that the Ice Age did not mean the entire planet was encased in ice. Far from it. Beyond the glittering, hostile margins of the glaciers, vast landscapes remained ice-free, supporting unique and often surprisingly rich ecosystems. Life didn't vanish during the glacial periods. It adapted, it migrated, and it persisted in these unglaciated refuges. Imagine standing at the southern edge of the Laurentide ice sheet, perhaps somewhere in what is now the Midwestern United States. Before you stretches not a lush forest, but a vast, open, windswept landscape. This is the periglacial zone, the land shaped by its proximity to the ice. The ground here is locked in permafrost, permanently frozen soil, perhaps extending hundreds, even thousands of feet deep. Only the top few inches thaw during the brief, cool summer, creating a boggy, unstable surface. The dominant vegetation here is tundra. Forget towering trees. This is a world of low-lying, hardy plants adapted to the extreme cold, the short growing season, and the frozen ground. Mats of mosses and lichens cling to the rocks. Tough sedges and grasses form tussocks across the landscape. Stunted dwarf willows and birches, perhaps only a few feet high, huddle in sheltered hollows, their branches twisted by the relentless wind blowing off the ice sheet. It is a stark, treeless, yet strangely beautiful world, painted in muted shades of green, brown, and grey during the summer, and buried under snow for much of the long winter. Further south, or in unglaciated regions like vast swathes of Siberia and Alaska, connected then by the Beringia land bridge, a different, unique, and now vanished ecosystem dominated the mammoth steppe. This was perhaps the most extensive biome on Earth during the last glacial maximum. It was not tundra, nor was it grassland as we know it today. It was a cold, dry, incredibly productive grassland dominated by highly nutritious grasses, herbs called forbs, and low shrubs. Imagine a vast open plain stretching further than the eye can see. The air is cold and dry. The ground is frozen for much of the year, but during the brief, intense summer, fueled perhaps by long hours of daylight at high latitudes, this landscape explodes with life. It supports immense herds of giant herbivores, the woolly mammoths, woolly rhinoceroses, bison, horses, reindeer, grazers perfectly adapted to this unique, cold-adapted grassland. This mammoth steppe was the foundation of the iconic Ice Age megafauna. Even further south, in regions far removed from the direct influence of the ice sheets, the climate was still profoundly affected. Temperate zones were cooler and often drier than they are today. Forests retreated towards the equator, replaced in many areas by open woodlands, savannas, or grasslands. Deserts expanded in the subtropical zones. The entire climatic map of the planet was redrawn by the presence of those great ice sheets in the north. These ice-free regions, the tundra, the mammoth steppe, the altered forests and grasslands further south, were the refugia, the places where life endured. They were not necessarily easy places to live. Conditions were often harsh, cold, and dry, but they were free from the crushing weight and scouring power of the glaciers. It was within these vast, unglaciated landscapes that the iconic drama of the Ice Age megafauna unfolded, and where our own human ancestors navigated a challenging but ultimately survivable world. The Ice Age was not just about the ice. It was equally about the vast, forgotten lands that existed beyond its reach. And the very air in these lands was different, carrying its own unique glacial signature. The vast ice sheets didn't just reshape the land and lower the seas, they fundamentally altered the very air that enveloped the planet. The atmosphere of the last glacial maximum was not just colder than our own, it was significantly drier and far, far dustier. Breathing the air of the Ice Age would have felt distinctly different, carrying the signature of a planet under the grip of a deep chill. The cold itself is the most obvious difference, with vast portions of the northern hemisphere buried under miles of ice, and global average temperatures perhaps 5 to 6 degrees Celsius lower than today. The world was simply a colder place. Winters were longer, harsher, extending further towards the equator. Even regions that remained ice-free experienced significantly cooler conditions, forcing plants and animals to adapt or migrate. But perhaps less intuitive is the profound dryness. Where did all the water go? It was locked up, frozen solid within those colossal continental ice sheets. Evaporation from the cold ocean surfaces was reduced. The immense ice sheets themselves acted like giant mountains, blocking the movement of moist air masses inland. As a result, precipitation levels plummeted across large parts of the globe. The interiors of continents became even more arid. Even regions that are wet and humid today, like parts of the Amazon rainforest, may have shrunk, replaced by drier savannas or grasslands. The world outside the immediate influence of melting glaciers was, in many places, a thirsty world. This combination of cold and dryness created the conditions for the third defining characteristic of the Ice Age atmosphere: dust. Imagine those vast, unglaciated landscapes, the tundra near the ice margins, the immense mammoth steppe stretching across Siberia and Beringia. The vegetation cover, though present, was often sparse compared to modern grasslands or forests. The ground, particularly during the long, dry winters or periods of drought, was exposed. And crucially, the glaciers themselves were immense factories of fine-grained sediment. As the ice flowed, it ground the underlying bedrock into a fine powder known as glacial flour or rock flour. Meltwater rivers, flowing milky white from beneath the ice sheets, carried vast quantities of this fine silt out onto the surrounding plains. Now add wind. The steep temperature gradients between the frigid ice sheets and the warmer lands to the south likely generated powerful, persistent wind systems. These winds, sweeping across the dry, sparsely vegetated landscapes and the vast plains covered in glacial flour, would have picked up enormous quantities of this fine dust. The result was an atmosphere significantly dustier than today, perhaps 10 to 20 times dustier. Great continent-spanning dust storms would have been a regular feature of the Ice Age world, perhaps lasting for days or weeks, filling the sky with a thick, choking haze, reducing visibility and blanketing the landscape in fine layers of silt. We see the evidence today in the vast deposits of loess, thick blankets of wind-blown silt that cover large parts of North America, Europe and Asia, geological remnants of those ancient dust storms. Breathing this air would have felt different, colder certainly, sharper, drier, perhaps irritating to the lungs and sinuses, and perceptibly dusty, carrying the fine mineral tang of the scoured continents. Even on a clear day, the sky might have possessed a slightly hazy, milky quality due to the high concentration of airborne particles. Sunsets might have been spectacularly red, the light scattering through the dusty air. This cold, dry, dusty atmosphere was the invisible envelope of the Ice Age world. It shaped the vegetation, influenced the climate, and presented its own unique challenges to the creatures breathing it. It was the air of a planet under stress, an atmosphere carrying the fine, gritty signature of a world dominated by ice. And as day turned into night in this altered world, the darkness brought its own unique character. As the cold, dusty day of the Ice Age draws to a close, the transition into night brings its own unique character, shaped by the celestial mechanics that govern the planet's rhythm and the stark realities of a world deep in the grip of a glacial period. The nights were not just colder, they were often longer, and the darkness they held possessed a different quality than the brief, warm nights of the greenhouse worlds we have visited before. The same Milankovitch cycles that drove the advance and retreat of the ice sheets also subtly influenced the length and intensity of the seasons. Changes in the Earth's axial tilt and the wobble of its axis altered the distribution of sunlight throughout the year. During glacial periods, these cycles often conspired to create winters in the northern hemisphere that were not only colder but also experienced longer periods of darkness, particularly at higher latitudes. Imagine the sun setting over a vast snow-dusted tundra landscape near the edge of the Great Laurentide ice sheet. The sunset itself might be brief, the sun a pale, weak disk dropping quickly below a horizon perhaps defined by the distant, glittering wall of the glacier itself. The twilight lingers perhaps, painting the immense ice-scoured sky in cold, pastel shades of pink and purple, reflected on the snow and ice. But the transition to full darkness feels swift, decisive, and the night, once fallen, stretches long. In the depths of winter, at latitudes significantly further south than today's polar circles, the darkness might have reigned for 16, 18, perhaps even 20 hours or more. It was a world dominated by night for a significant portion of the year. This prolonged darkness profoundly shaped the lives of the creatures inhabiting this world. Plants entered deep dormancy. Many animals likely hibernated, seeking refuge in burrows or dens to wait out the long, cold, dark months. For those active year-round, like the mammoths, woolly rhinos, or the predators that hunted them, life became a constant struggle against the cold and the lack of light. Finding food in the frozen, snow-covered landscape under a sky offering only faint starlight or moonlight would have been an immense challenge. For our hypothetical human observer, experiencing this extended night would be deeply unsettling. Accustomed to the relatively balanced cycle of day and night in our modern world, the sheer, unrelenting duration of the Ice Age winter night would feel oppressive. It amplifies the sense of isolation, the feeling of being trapped in a cold, hostile darkness with no end in sight. The very quality of the darkness might have felt different too. While the dense canopy of the Cretaceous forest created an absolute suffocating blackness, the open landscapes of the Ice Age tundra or steppe might have offered a different kind of night. On clear nights, free from the thick humidity of earlier eras, the sky could have been vast, cold, and perhaps startlingly clear, the stars blazing with an intensity rarely seen through modern, thicker atmospheres. Moonlight reflecting off endless expanses of snow or pale, dry grasses might have cast the landscape in a ghostly, silvered monochrome, creating long, stark shadows. But this faint illumination offered little comfort. It merely revealed the vast emptiness, the profound silence of the frozen world. It was a darkness that felt immense, ancient, and deeply indifferent. And within this long, cold night, the very sounds of the planet took on a different, sharper, more resonant quality. The long, deep darkness of the Ice Age night was not necessarily silent. While it lacked the dense, multi-layered chorus of a tropical swamp, this cold, open world possessed its own unique and often haunting soundscape, a symphony played on instruments of wind, ice, and distance. Listening in the profound stillness beneath a sky perhaps ablaze with cold, distant stars, one would hear the planet breathing in a different register. The most constant presence was likely the wind, sweeping unimpeded across the vast, treeless expanses of tundra and mammoth steppe, or pouring down off the colossal ice sheets as frigid katabatic gales. The wind would have been a near-constant companion. It wouldn't necessarily be a violent storm, but a persistent, deep howl or moan vibrating through the frozen air. It was the sound of emptiness, the sound of immense space, carrying with it the fine, sharp particles of snow or dust, perhaps whistling eerily around the few exposed rock formations or the bones of long-dead giants. It was a sound that spoke of relentless, penetrating cold. Interspersed with the wind's cry would be the sounds of the ice itself. Glaciers, even seemingly static ones, are rivers of solid water, constantly shifting, flowing, and adjusting under their own immense weight. From the direction of the great ice sheets, perhaps miles away, deep, resonant groans and creaks might travel through the cold, dense air, the sound of millennia of compressed ice settling and moving. More dramatically perhaps, sharp cracks, like distant rifle fire, might echo across the landscape as temperature fluctuations caused fissures to open within the ice, or as great sections prepared to carve off into unseen proglacial lakes or the frigid ocean. It was the sound of geological forces at work, slow, powerful, and utterly indifferent. And then there were the sounds of life, though likely sparser, more distant, and perhaps carrying further in the clear, cold air than in a dense forest. Far off, perhaps miles away, the deep, resonant rumble or trumpet-like call of a herd of woolly mammoths might drift on the wind, a low, almost subsonic vibration hinting at their immense presence on the landscape. Closer, perhaps, the sharp, sudden snort of a woolly rhinoceros disturbed in the darkness, or the high-pitched bark of an Arctic fox hunting lemmings beneath the snow. And sometimes, more chillingly, the sounds of the predators. The long, mournful howl of a pack of dire wolves echoing across the frozen plains, their calls carrying for immense distances in the still air, or perhaps the deep, guttural cough or snarl of a saber-toothed cat, brief, menacing, and instantly silencing any smaller sounds nearby. These were not constant sounds, but sudden, sharp intrusions into the background hum of wind and ice, stark reminders that even in this frozen world, the ancient drama of hunter and hunted continued through the long night. The overall impression of the Ice Age night soundscape is one of vastness, emptiness, and punctuated moments of distant life. It lacks the overwhelming, close proximity buzz of the Cretaceous night. Instead, it is a soundscape defined by distance, by clarity, and by the profound, underlying silence of a world held fast by cold. It is a soundscape that speaks less of teeming life and more of endurance, of solitude, and of the immense, indifferent power of the elements. And the most powerful of those elements, the cold itself, made its presence felt not just in the air, but in every breath, every surface, every moment. The long hours of darkness during the Ice Age winter were not just visually empty. They were defined by a cold so profound, so penetrating, that it became the central, inescapable reality of existence. This was not the invigorating chill of a crisp autumn morning, or the manageable cold of a modern winter buffered by insulated homes and warm clothing. This was a deep, pervasive, and often lethal extreme cold, a fundamental force that shaped the land, the life, and the very air itself. Imagine stepping out into that night, away from the hypothetical warmth of a fire or the shelter of a cave. The temperature drop would be immediate and brutal. While average global temperatures were lower, the true signature of the Ice Age was in its extremes. In the heart of winter, particularly at higher latitudes or near the great ice sheets, temperatures could plummet to levels rarely experienced outside the polar regions today. -30 degrees Celsius, -22 Fahrenheit, -40 Fahrenheit, perhaps even lower on the vast continental interiors or atop the ice sheets themselves. At these temperatures, the air itself feels different. It becomes sharp, almost crystalline. Breathing in feels like inhaling tiny needles of ice. The moisture in your breath would freeze instantly upon exhaling, creating a cloud of glittering ice crystals, a phenomenon known as ice fog or diamond dust, hanging silently in the still air. Your nostrils would sting, the delicate membranes freezing with each intake of the frigid air. Exposed skin would become numb within minutes, the blood retreating, the first dangerous sign of frostbite setting in with alarming speed. It's a cold that feels less like a temperature and more like a physical presence, actively stealing the heat from your body. The ground beneath your feet would be frozen solid, hard as iron. Any moisture within the soil locked into permafrost, perhaps extending thousands of feet down. Lakes and rivers would be sealed under thick layers of ice, their surfaces perhaps cracked and groaning under the immense thermal stress. Even the great oceans, while not freezing solid, would see vast expansions of sea ice extending far south from the Arctic, choking coastlines and altering marine ecosystems. Water, the essential ingredient for life, becomes a precious, elusive commodity in this frozen world. Finding liquid water might require seeking out geothermally heated springs or painstakingly melting snow or ice, a process demanding precious energy in a world where energy conservation is paramount. Even the snow itself might be different. Not always the soft, fluffy powder of a gentle snowfall, but perhaps often fine, dry, wind-driven crystals, scouring the landscape like sand, accumulating in deep, sculpted drifts, or forming hard, impenetrable wind crusts on the surface. This extreme cold was a constant, relentless pressure on life. Survival demanded extraordinary adaptations. The thick, shaggy fur of the woolly mammoths and rhinos, the dense layers of blubber insulating marine mammals, the evolutionary drive towards larger body sizes, Bergmann's rule, minimizing heat loss relative to volume, the instinct to hibernate, to burrow deep beneath the frost line, entering a state of suspended animation to wait out the worst of the winter. For our hypothetical human observer, enduring even a short exposure to this level of cold without the sophisticated gear and knowledge of Ice Age peoples would be lethal. The body's core temperature would plummet rapidly. Hypothermia would set in quickly, leading to confusion, lethargy, and ultimately a quiet, frozen end. The cold was the defining characteristic, the background state of the Ice Age night. It shaped the sounds, influenced the movements of animals, and dictated the very possibilities of survival. It was a silent, invisible, and utterly uncompromising force, demanding respect, adaptation, or surrender. And yet, even in this profound chill, the sky above sometimes offered its own cold, ethereal fire. As you endure the profound cold and the immense darkness of the Ice Age night, your eyes, straining against the blackness, might occasionally be rewarded with a spectacle of truly celestial proportions, a silent, shifting ballet of light painting the heavens. The aurora borealis, or northern lights, a phenomenon we typically associate with the high Arctic latitudes today, may have been a far more common and perhaps far more southerly visitor to the night skies of the glacial world. What causes this ethereal display? It begins, not on Earth, but nearly 93 million miles away, at the heart of our solar system, the Sun. The Sun is not a static, burning ball. It constantly emits a stream of charged particles, electrons and protons, known as the solar wind. This wind flows outwards through space at incredible speeds. Our planet possesses a powerful defense against this constant bombardment, its magnetic field. Generated by the churning molten iron core deep within the Earth, this magnetic field extends far out into space, forming an invisible shield called the magnetosphere. Most of the solar wind particles are deflected harmlessly around our planet by this shield. However, near the Earth's magnetic poles, north and south, the field lines dip inwards, creating funnels. Some of the charged particles from the solar wind become trapped within these funnels and are channeled down towards the upper atmosphere at high speeds. And here, perhaps 60 to 200 miles above the ground, the magic happens. These high-energy particles collide with the atoms and molecules of gas in our own atmosphere, primarily oxygen and nitrogen. These collisions excite the atmospheric gases, temporarily boosting their electrons to higher energy levels. As these electrons inevitably fall back to their normal state, they release that excess energy in the form of tiny flashes of light, photons. Multiply these microscopic flashes by trillions upon trillions, occurring across vast regions of the upper atmosphere, and the result is the aurora. Shimmering curtains, pulsating arcs, and shifting rays of colored light dancing across the night sky. The specific colors depend on which gases are being excited and at what altitude. Oxygen typically glows green or red, while nitrogen can produce blues and purples. Now, why might these displays have been more common or visible further south during the Ice Age? The key lies in the behavior of the Earth's magnetic field itself. The magnetic poles are not fixed, they wander over geological time, and the overall strength of the magnetic field also fluctuates. Some evidence suggests that during parts of the last glacial period, the magnetic field might have been slightly weaker, or the magnetic poles might have been situated in slightly different locations compared to today. A weaker field, or poles shifted perhaps closer to geographical latitudes where people and animals lived, could have allowed the solar wind particles to penetrate deeper into the atmosphere, or reach lower latitudes more easily, triggering auroral displays visible across regions that rarely, if ever, see them now. Imagine skies above Ice Age France, or perhaps even the northern plains of America, periodically illuminated not just by stars, but by the silent, shifting green and red glow of the aurora. Picture the scene. The vast, snow-covered tundra lies silent beneath a canopy of brilliant, cold stars. The wind howls softly in the distance, and rippling across the northern horizon, perhaps even stretching overhead, are vast, silent curtains of ethereal light. They shift, they brighten, they fade, a celestial dance performed in utter silence. To the early humans who witnessed these displays, huddled perhaps near the flickering warmth of a fire, they must have seemed truly magical, terrifying, or profoundly spiritual. Messages from the gods, spirits dancing in the sky, or simply an inexplicable, awe-inspiring fire in the heavens. Even for our hypothetical modern observer, witnessing such a display in the profound silence and emptiness of the Ice Age night would be an experience of breathtaking beauty and deep cosmic awe. It is a reminder that even in the depths of a planetary winter, the universe continues its intricate dance, connecting the fires of the sun to the thin air of our own world in a display of silent, cold, and utterly magnificent light. And beneath these potentially shimmering skies, the familiar patterns of the stars themselves offered a slightly different map. As you gaze upwards into the immense, clear, and profoundly dark sky of the Ice Age night, perhaps fortunate enough to witness the silent dance of an aurora, perhaps simply lost in the sheer, overwhelming multitude of stars, another subtle difference might begin to register, a quiet sense of disorientation for anyone familiar with the modern night sky. The stars themselves, while intrinsically the same, would appear arranged in slightly different patterns. The celestial map has shifted. This is due to a slow, graceful, and incredibly long-term wobble in the Earth's axis, a phenomenon known as axial precession. Imagine the Earth spinning like a top. As it spins, its axis doesn't remain perfectly fixed in orientation relative to the distant stars. Instead, it slowly traces out a large circle in the sky, much like a spinning top begins to wobble as it slows down. This wobble is incredibly slow, taking roughly 26,000 years to complete just one circle. But over the timescales we are dealing with, tens of thousands of years since the peak of the last glacial maximum, this slow drift has a noticeable effect. It changes which star happens to be the North Star and subtly shifts the apparent positions of all the constellations relative to the seasons. Today, our north celestial pole points almost directly at Polaris, the familiar North Star, a reliable anchor in the northern sky. But 15,000 or 20,000 years ago, during the heart of the Ice Age, Polaris was just an ordinary star located far from the pole. The North Star of that time might have been a different, perhaps fainter star, maybe one within the constellation Hercules or Lyra, like the bright star Vega, though Vega was closer to the pole much earlier. Or perhaps there was no bright star conveniently marking true north at all, making celestial navigation a different kind of challenge. The familiar constellations, those patterns we trace in the stars, Orion, the Big Dipper, Cassiopeia, would have still been recognizable. The stars themselves are so incredibly distant that their positions relative to each other change almost imperceptibly over human timescales. But their position in the sky at different times of the year would have been different. Constellations we associate with winter today might have been prominent in the summer sky back then, and vice versa. The entire celestial calendar was shifted. Imagine lying on the frozen ground, looking up at that vast, cold tapestry. You might recognize Orion, the great hunter, striding across the sky. But perhaps he appears at a different time of night, or hangs at a different angle over the horizon than you are used to. The familiar celestial landmarks are subtly out of place, adding another layer to the profound sense of temporal dislocation. This shifted sky serves as a quiet, cosmic reminder of the immense timescale we are exploring. The very stars, which seem so eternal, so fixed in our fleeting human perspective, are participants in this slow, grand, celestial dance. The view from Earth is never static. To the early humans living under this sky, these specific star patterns would have been their normal. They would have woven their own stories, their own mythologies, into these slightly different arrangements. They would have navigated by these stars, marked the passage of seasons by their movements. It was their map, their clock, their connection to the cosmos. For you, the hypothetical time traveler, it is another subtle yet profound source of unease. Even the seemingly eternal stars offer no familiar comfort, no fixed point of reference. They too whisper of the immense gulf of time that separates you from your own world. The sky itself confirms your status as a visitor, an observer of a world operating under a different celestial clock. And somewhere, perhaps not far away in the cold darkness beneath these ancient stars, the faint flickering light of a different kind of presence might be found. Amidst the vast, profound, and often intimidating silence of the Ice Age night, broken only by the howl of wind or the distant call of a mammoth, another sound, infinitely smaller yet carrying a profound significance, might occasionally be heard. It is the soft crackle of a fire, and perhaps, carried on the frigid air, the faintest, most fleeting scent of wood smoke. These are the subtle signatures of the other intelligent creature navigating this frozen world. Early humans. We must tread carefully here. Our journey is one of sensory immersion into the environment of the Ice Age, a meditation for sleep, not a dramatic retelling of human survival struggles, but to ignore the presence of our own ancestors who shared this world with the mammoths and the glaciers would be to omit a crucial, poignant element of the nocturnal landscape. Imagine, perhaps from a high vantage point, looking out across miles of dark, snow-dusted tundra under the cold starlight. Most of the landscape is a uniform, deep black. But then, far off, almost imperceptibly small, you might see it, a tiny, flickering pinprick of orange light, a campfire. It is a minuscule beacon against the immense darkness, a fragile assertion of warmth and presence in a world dominated by cold. It speaks of shelter, perhaps a shallow cave, a rock overhang, or a simple encampment built from mammoth bones and hides. It speaks of community, a small band of hunter-gatherers huddled together against the long night. What sounds might emanate from such a place, heard from a safe distance? Not loud shouts or songs, perhaps. The night demands caution. But maybe the low, indistinct murmur of voices speaking a language lost to time. Perhaps the sharp crack of a log settling on the fire, or the faint, rhythmic scraping sound of someone working flint, preparing tools for the next day's hunt. These are human sounds, yet rendered ancient and mysterious by the immense gulf of time. And the scent, wood smoke, that uniquely human signature on the landscape, might carry for miles on the cold, dry air. It is a smell vastly different from the damp decay of the Cretaceous swamp or the mineral tang of the earlier Earth. It is the smell of controlled combustion, of technology, however simple. It is a smell that signals warmth, cooking, and the presence of minds capable of shaping their environment. To our hypothetical modern observer, stumbling upon such a scene, even imaginatively from a safe distance, would be profoundly moving. It is the first faint echo of ourselves in this deep past. It is a reminder that we too are creatures forged by the Ice Age, that our own resilience, our own ingenuity, our own capacity for cooperation was honed in these very landscapes under these very stars. But it is also a reminder of the fragility of that existence. That tiny fire is a precarious hold against the overwhelming cold and darkness. The murmur of voices is a small sound against the vast silence. The presence of these early humans does not diminish the wildness or the danger of the Ice Age night. It underscores it. They were not rulers of this world, not yet. They were participants, survivors, carving out their existence within a kingdom still dominated by ice and giants. We will not dwell on their hunts, their struggles, or their art in this journey. Our focus remains on the atmosphere, the environment itself. But acknowledging their presence, even as a faint flicker in the distance, adds a final, poignant layer to the nocturnal tapestry. It reminds us that even in the deepest freeze, the spark of human consciousness was already alive, watching the same ancient stars, listening to the same howling wind, and waiting, like all life, for the eventual return of the sun. The great cycles continued, shaping not just the land, but the very oceans themselves. While the great ice sheets were the most visible, most dramatic expression of the Ice Age's power, their influence extended far beyond the lands they directly crushed. Their very existence was predicated on a planetary-scale act of theft, a theft of water from the single vast reservoir that connects all continents, the global ocean. The Ice Age didn't just freeze the land, it drained the seas. Think of the Earth's water budget as largely a closed system. The total amount of water on the planet, in oceans, lakes, rivers, groundwater, ice caps, and the atmosphere, remains relatively constant over geological time. It simply moves between these different reservoirs. During warm, interglacial periods, like our own, most of this water resides in its liquid form, primarily in the vast ocean basins. Ice is confined mainly to the polar caps of Antarctica and Greenland, and to high mountain glaciers. But during a glacial maximum, this balance shifts dramatically. As the climate cools, more precipitation falls as snow rather than rain, particularly at high latitudes. And crucially, the snow that falls in the regions where the great ice sheets are growing does not melt in the summer. Year after year, century after century, snowfall accumulates, compressing under its own weight, transforming into dense glacial ice. This ice is built, quite literally, from ocean water. The water evaporates from the sea surface, travels through the atmosphere as vapor, falls on the nascent ice sheets as snow, and then it stays there, locked away, frozen solid, sometimes for tens of thousands of years. It is water that has been removed from the active hydrological cycle, subtracted from the liquid oceans. The sheer scale of the Laurentide and Fennoscandian ice sheets, along with expanded glaciers worldwide, meant that an almost inconceivable volume of water was sequestered in this way. It was as if the planet had siphoned off a significant portion of its oceans and stored it, frozen upon the land. The consequence was inevitable. Global sea levels plummeted. As more and more water became locked up in the growing ice sheets, the level of the world's oceans dropped dramatically. During the peak of the last glacial maximum, around 20,000 years ago, global average sea level is estimated to have been about 120 meters, or nearly 400 feet, lower than it is today. Pause for a moment to truly absorb that figure. 400 feet. Imagine the coastline near where you live. Now imagine the ocean withdrawing, retreating outwards, exposing land that is currently submerged beneath 400 feet of water. This wasn't a subtle change. It was a radical redrawing of the world map. Vast areas of the shallow continental shelves, the gently sloping underwater margins of the continents, were transformed into dry land. Coastlines migrated tens, sometimes hundreds, of miles seaward. Islands became connected to the mainland. Shallow seas became fertile plains. This immense drop in sea level was one of the most profound global signatures of the Ice Age. It created entirely new landscapes, opened up migration routes for animals and early humans, and fundamentally altered the relationship between land and sea across the entire planet. The oceans didn't truly go anywhere. They simply shrank, their waters drawn up and frozen into the colossal ice monsters that dominated the northern continents. The The familiar coastlines we know today are merely the high water mark of our current, warm, interglacial period. The true extent of the continents, revealed during the Ice Age, included vast, forgotten territories that now lie submerged once more, holding the secrets of a time when the oceans themselves seemed to have withdrawn in deference to the power of the ice. And it was upon these newly exposed lands that some of the Ice Age's most fascinating stories unfolded. The dramatic fall in sea level, that 400-foot global withdrawal of the oceans, did more than just shift coastlines outwards. It performed a kind of geological magic trick. It revealed vast hidden landscapes, land bridges that connected continents previously separated by water. These were not narrow, precarious isthmuses, but immense, habitable plains, forgotten worlds that played a crucial role in the story of Ice Age life, including our own human journey. Two of these lost lands stand out in particular: Beringia and Doggerland. Let us first travel north, to the place where the old world met the new. Today, the Bering Strait is a narrow, frigid body of water separating Siberia from Alaska, a gap of about 55 miles. But during the last glacial maximum, with sea levels drastically lower, this strait did not exist. In its place emerged a vast, unglaciated landmass known as Beringia. Imagine a subcontinent stretching perhaps 1,000 miles from north to south, connecting the northeastern tip of Asia with the northwestern edge of North America. This was not a barren, icy wasteland. While glaciers covered much of North America further south and east, Beringia itself remained largely ice-free, perhaps due to extremely dry conditions preventing large-scale snow accumulation. It was a unique landscape, the Mammoth Steppe. Cold, yes, windswept, undoubtedly, but covered not in tundra mosses, but in a dry, nutrient-rich grassland, dotted perhaps with hardy shrubs and dwarf willows. This steppe thrived under the unique Ice Age conditions: long, cold, dry winters, but brief, intense summers with almost continuous daylight, fueling rapid plant growth. And this productive grassland supported immense herds of Ice Age megafauna: woolly mammoths, woolly rhinoceroses, steppe bison, wild horses, and the predators that hunted them: saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Saber-toothed cats, short-faced bears, dire wolves, and the predators that hunted them. Wolves all roamed across this vast, lost bridge. For tens of thousands of years, Beringia served as a crucial refuge and a migration corridor. Animals moved back and forth between Asia and North America, shaping the unique faunal mix of both continents. And crucially, it was across this land bridge that the first humans are thought to have journeyed into the Americas, following the herds, unknowingly stepping onto a new world. Beringia was not just a bridge, it was a destination, a lost world with its own unique ecosystem, swallowed by the rising seas as the ice melted, its memory preserved only in the fossil record and the genetic heritage of two continents. Now let us travel halfway around the world to northwestern Europe. Today, the North Sea separates Great Britain from the European mainland. But during the Ice Age, this sea too vanished. In its place emerged another vast, lost land, Doggerland. Imagine standing on the coast of what is now England and looking east. You see not water, but a vast, low-lying plain stretching towards Denmark and the Netherlands. Doggerland was perhaps less stark than Beringia, likely a landscape of rolling hills, meandering river valleys, marshlands, and perhaps even open woodlands. It was a rich and fertile land, warmed slightly by the influence of the Atlantic currents even during the glacial period. Fossil evidence, dredged up by fishing trawlers from the bottom of the North Sea, reveals that Doggerland supported a diverse ecosystem. Mammoths, woolly rhinos, giant deer, reindeer, and horses roamed its plains. Its rivers teemed with fish. And significantly, archaeological finds, finely crafted flint tools, barbed harpoons made of bone, tell us that Mesolithic humans inhabited this land extensively. Doggerland was not just a bridge, it was a heartland, a rich, productive landscape that was home to thriving human populations for thousands of years. But like Beringia, its existence was temporary, tied to the low sea levels of the Ice Age. As the great ice sheets melted, beginning around 12,000 years ago, the rising waters of the North Sea began to creep back. What was once a vast plain became a shrinking landscape of hills and islands. Perhaps catastrophic floods, like the Storegga Slide tsunami around 8,200 years ago, accelerated its demise. Eventually, the last high points were submerged and Doggerland vanished beneath the waves, becoming a prehistoric Atlantis, its memory surviving only in scattered artifacts and the lingering folktales of lands lost to the sea. These two great land bridges, Beringia and Doggerland, are perhaps the most dramatic examples of the forgotten landscapes revealed by the Ice Age's low seas. They were vast, habitable worlds, crucial corridors for life, teeming with unique ecosystems, only to be reclaimed by the ocean as the planet warmed. They are silent reminders that the map we know is merely a snapshot in time, and that beneath the waves lie entire worlds waiting to be remembered. Let us linger for a moment on one of these great lost lands revealed by the Ice Age's low seas, Beringia. This vast subcontinent connecting Siberia and Alaska was more than just a corridor. It was a unique and enduring ecosystem, a world sculpted by cold, dryness, and immense herds of giant animals. To understand the Ice Age, we must understand the mammoth steppe. Forget the popular image of a barren, snow-blasted wasteland. While Beringia was certainly cold, nestled between the Pacific Ocean, the Arctic Ocean, and the towering ice sheets further south, it was also incredibly dry. The massive Laurentide ice sheet acted like a colossal mountain range, creating a rain shadow that blocked moisture-laden Pacific storms from reaching the interior. Precipitation levels were extremely low, perhaps comparable to modern-day Arctic deserts. This profound dryness prevented the formation of large glaciers within Beringia itself, leaving the land largely ice-free. And in this cold, dry environment, a unique type of vegetation flourished. It was not the mossy, boggy tundra we associate with the Arctic today. It was a vast, productive grassland, dominated by highly nutritious grasses, sedges, and, crucially, a diverse array of forbs, non-grassy flowering plants, similar perhaps to the wildflowers found in modern alpine meadows. This mixture of grasses and protein-rich forbs created an incredibly fertile grazing landscape, far more productive than modern tundra. Imagine looking out across this landscape during the brief, intense summer. The sun, perhaps circling low in the sky for nearly 24 hours at these high latitudes, bathes the immense plain in a cool, bright light. The ground is a carpet of green and perhaps subtle, hardy flowers, stretching to a vast, unbroken horizon. There are few trees, perhaps only stunted willows and birches clinging to the sheltered river valleys. The dominant impression is one of immense openness, a landscape defined by wind, grass, and sky. The air is cold, crisp, and incredibly dry. The wind is a constant presence, sweeping across the plains, perhaps carrying the fine glacial dust that characterized the Ice Age atmosphere. In the winter, this same landscape would transform into a stark, frozen desert, buried under a relatively thin layer of wind-swept snow. And upon this vast productive steppe lived the titans of the Ice Age. This was the heartland of the woolly mammoth. Immense herds, numbering perhaps in the thousands, would have migrated across these plains, their great curved tusks used perhaps to sweep aside snow in search of buried grasses, their shaggy coats providing insulation against the bitter cold. Alongside them grazed other giants, the woolly rhinoceros, a solitary formidable herbivore. Vast herds of steppe bison, larger and perhaps shaggier than their modern cousins. Herds of wild horses, adapted to the cold and dryness, and countless reindeer or caribou. This incredible abundance of large herbivores in turn supported a fearsome array of predators. Packs of dire wolves, larger and more robust than modern grey wolves, would have hunted the bison and horses. The scimitar-toothed cat, Homotherium, a specialized mammoth hunter perhaps, stalked the herds. And the colossal short-faced bear, Arctodus simus, perhaps the largest terrestrial mammalian predator of the time, may have acted as both hunter and intimidating scavenger. This entire unique ecosystem, the cold-adapted grasses and forbs, the immense herds of grazers, the specialized predators, is known as the mammoth steppe. It existed with regional variations across vast swathes of the unglaciated northern hemisphere during the glacial periods, from Europe eastward across Siberia, over Beringia and into Alaska and the Yukon. Beringia was perhaps its largest, most stable and most enduring expression. It was a world born of ice, yet free of ice. A world defined by cold, yet teeming with giant life. It was the crucial link between continents, the highway for migration, and a unique, forgotten ecosystem in its own right. Understanding the mammoth steppe is essential to understanding the true character of the Ice Age world, a world far more complex and dynamic than just endless ice and snow. And just as Beringia connected continents in the north, another lost land held sway in the temperate latitudes of Europe. Let us now shift our focus southward and westward, leaving the cold, dry expanse of the mammoth steppe behind, and travel to the other great landmass revealed by the Ice Age's low seas, Doggerland. This vast territory, now submerged beneath the cold waves of the North Sea, was not a stark Arctic plain, but a temperate landscape, a lost heartland connecting Great Britain to mainland Europe. Imagine standing on a gently rolling hill somewhere between modern-day England and Denmark 20,000 years ago. The air here is cool, perhaps comparable to a modern-day northern European autumn or spring, but noticeably drier than today. While the colossal Fennoscandian ice sheet looms far to the north, its direct influence here is less intense. This land is entirely free of ice. The landscape stretching out before you is not one of endless grass, like Beringia. Doggerland was likely a complex mosaic of different habitats, vast plains dominated by grasses and sedges, yes, similar perhaps to the mammoth steppe, but less extreme in their cold and dryness. But these plains were likely interspersed with significant areas of open woodland, perhaps birch, pine, and willow groves clinging to river valleys or sheltered slopes, and meandering through this landscape were great river systems, the ancient combined courses of the Rhine, the Thames, and the Seine, flowing slowly across the low-lying plain towards a coastline far to the north and west of where it lies today. Extensive marshlands and estuaries likely fringed these rivers and the distant coast. It was a landscape richer, perhaps more varied, and certainly less harsh than the high-latitude steppe, and it supported its own distinctive community of Ice Age life. Woolly mammoths undoubtedly roamed here too, perhaps in smaller numbers or with slightly different adaptations than their Beringian cousins. Woolly rhinoceroses were present. Herds of reindeer, wild horses and bison grazed the open plains. In the woodlands, perhaps giant deer, the megalocaros, browsed, their immense antlers navigating the trees. The predators were here as well, packs of wolves, cave hyenas, perhaps the European cave lion, a formidable hunter larger than its modern African relative, and undoubtedly early humans. Doggerland was not just a bridge, it was prime real estate. Its relatively milder climate compared to the lands closer to the ice, its diverse habitats and its abundant freshwater sources made it an incredibly attractive territory for both animals and the Mesolithic hunter-gatherers who followed them. The evidence for this vibrant ecosystem lies scattered across the floor of the North Sea today. Fishing trawlers, dragging their heavy nets across the seabed, frequently bring up astonishing artifacts: fossilized mammoth tusks and rhino bones, beautifully crafted barbed harpoons made from antler, flint tools, sharpened axes, fragments of human settlements. These finds are tangible proof of a lost world, a prehistoric breadbasket teeming with life. Doggerland represents a different facet of the Ice Age world. Not the extreme cold of the high Arctic steppe, but a cooler, drier version of temperate Europe. A landscape teeming with familiar, though often larger creatures and significantly our own human ancestors. It was a world perfectly habitable, intensely utilized, and deeply familiar to those who lived there. But its existence was entirely dependent on the vast quantities of water locked away in the distant ice sheets. Its very foundation was borrowed time. As the planet inevitably began to warm, as the glaciers began their slow retreat, the fate of Doggerland was sealed. The rising waters would return, reclaiming this lost heartland, submerging its hills, its rivers, and the memories of the creatures and people who had called it home. Its story is a poignant reminder of the dramatic and sometimes rapid transformations our planet is capable of. And these changes weren't just confined to the land. The oceans themselves were undergoing their own quiet revolution. While the shrinking coastlines and emerging land bridges were the most dramatic visual consequences of the Ice Age's grip on the world's water, the oceans themselves, the vast volumes of liquid water that remained, were also undergoing profound transformations. The Ice Age didn't just lower the seas, it changed their temperature, their circulation, and the very nature of the life they could support. The most immediate change was simply temperature. With global average temperatures significantly lower, the oceans cooled accordingly. Tropical regions remained relatively warm, but their extent likely shrank. Temperate and polar waters became considerably colder. Vast areas of the northern oceans, like the North Atlantic and Arctic Ocean, were choked with sea ice, far more extensive than today. This seasonal or even year-round sea ice cover would have dramatically altered light penetration, salinity, and the ability of marine life to thrive in these regions. Imagine coastlines fringed not with beaches, but with frozen sea spray and grinding pack ice. This widespread cooling forced marine life to migrate. Species adapted to warmer waters retreated towards the equator, their habitable zones shrinking. Cold-adapted species, like certain types of seals, whales, ancestors of modern Arctic whales perhaps, and fish, flourished and expanded their ranges. The entire biogeographical map of the oceans was redrawn by the advancing cold. The lowered sea levels also had a direct impact on ocean circulation. Ocean currents are like great rivers within the sea, transporting heat, nutrients, and life around the globe. They are steered and channeled by the shape of the ocean basins and the configuration of the continents. When sea levels dropped by 400 feet, shallow seaways that today allow water to flow between ocean basins either disappeared completely or became significantly restricted. Passages like the Bering Strait closed, forming the Beringia land bridge, and perhaps connections through the Indonesian archipelago were severed or narrowed. This would have fundamentally altered the pattern of global ocean currents. The flow of water between the Pacific and Arctic, or between the Indian and Pacific Oceans, would have changed, potentially impacting heat transport and climate patterns on a global scale. The ocean's circulatory system was operating under a different configuration. Furthermore, the presence of the massive ice sheets themselves influenced ocean currents. Cold, dense meltwater flowing off the edges of the glaciers into the sea would have sunk, contributing to deep water formation and potentially altering the Great Thermohaline Circulation, the global ocean conveyor belt. Winds blowing off the ice sheets would have also driven surface currents in different patterns. Were these colder, lower oceans less productive? Not necessarily. While tropical diversity may have decreased, the colder waters could hold more dissolved gases, including oxygen. Additionally, strong winds blowing off the continents, perhaps carrying that iron-rich glacial dust, could have fertilized certain areas of the ocean, fueling plankton blooms. And near the edges of the great ice sheets and sea ice zones, a unique and potentially highly productive ecosystem might have existed, driven by seasonal melting and nutrient upwelling, similar to the vibrant ecosystems found near Antarctica today. The oceans of the Ice Age were not static, frozen deserts. They were dynamic, altered systems. Colder, yes. Lower, certainly. Circulating differently, undoubtedly. But still teeming with life, albeit a life adapted to the specific, challenging conditions of a world in the grip of ice. They were a different kind of forgotten ocean, not vanished entirely like Mirovia or the Western Interior Seaway, but transformed, holding their own secrets beneath a colder, greyer sky. And the coastlines revealed by their retreat offered new opportunities and new challenges for the creatures living at the boundary of land and sea. The retreat of the oceans, that 400-foot drop in global sea level, did more than just reveal vast land bridges connecting continents. It fundamentally transformed the coastlines themselves, exposing immense tracts of the continental shelf and creating entirely new habitats at the interface between land and sea. Life, ever adaptable, quickly moved to colonize these newly available territories, creating unique coastal ecosystems shaped by the cold, the wind, and the proximity to the shrunken ocean. Imagine standing on a coastline during the last glacial maximum. The beach is far broader than the one you know today, stretching perhaps for miles before meeting the cold grey water. The land emerging from the sea is not necessarily dramatic cliffs or sandy dunes. It is often a low-lying, gently sloping plain, the former seabed now exposed to the harsh Ice Age air. What kind of life thrived here? These newly exposed coastal plains, while often cold and windswept, could also be surprisingly productive. Rivers extending their courses across the emergent shelf to meet the distant sea would carry nutrients from the land. The proximity to the ocean might moderate the extreme cold experienced further inland. In many regions, these coastal plains likely supported extensions of the mammoth steppe or tundra ecosystems found further inland. Hardy grasses, sedges and forbs would have colonized the former seabed, providing grazing for herds of bison, horses, reindeer, and perhaps mammoths venturing down from higher ground. These coastal steppes might have been particularly important grazing areas, perhaps offering slightly longer growing seasons or different types of vegetation compared to the continental interior. Near the shore itself, a specialized community adapted to the marine influence would have flourished. Vast colonies of seabirds, perhaps nesting on newly exposed rocky outcrops or islands that were once submerged reefs, would have filled the air with their calls. Their modern descendants still follow similar patterns, concentrating in immense numbers where ocean currents bring nutrients to the surface. Seals and sea lions, ancestors of modern cold-adapted pinnipeds, would have hauled out onto these broad new beaches, perhaps in vast rookeries, breeding and raising their young safe from purely terrestrial predators. The cold, nutrient-rich waters just offshore likely supported abundant fish stocks, providing a reliable food source. Even walruses, with their specialized tusks for foraging on bottom-dwelling shellfish, might have found new, productive feeding grounds in the shallower waters covering parts of the exposed shelf. And for humans, these coastal plains offered a unique set of resources. They provided access to both terrestrial game migrating across the steppes and abundant marine resources: seals, seabirds, shellfish, fish along the shore. Archaeological evidence suggests that many early human populations thrived in these coastal environments, exploiting the rich boundary between land and sea. The now submerged landscapes of Doggerland, for instance, show ample evidence of extensive human occupation precisely because it offered such a rich coastal habitat. Life on these Ice Age coastlines was shaped by the unique conditions: the expanded land area, the colder waters, the strong winds, and the abundance of both terrestrial and marine life. It was a dynamic, productive, yet challenging environment. These vast coastal plains, now lost beneath the waves, represent another forgotten landscape of the Ice Age. They were not just empty spaces revealed by the retreating water, they were vibrant ecosystems in their own right, crucial habitats that supported unique communities and served as vital corridors for migration. They are a reminder that the Ice Age world was not monolithic, but a complex mosaic of interconnected environments, each with its own story, its own inhabitants, and its own secrets now resting beneath the sea. And inland, beyond these coasts, the most iconic inhabitants of the age played out their own dramas of survival. When we conjure images of the Ice Age megafauna, one creature inevitably looms largest in our imagination: the woolly mammoth. With its immense size, its shaggy coat, its dramatically curved tusks, it has become the undisputed icon, the very symbol of this lost, frozen world. And rightly so. These magnificent giants roamed in vast herds across the mammoth steppe, shaping their environment and captivating our human ancestors. But the Ice Age was not solely the age of mammoths. The supporting cast, the other giants that shared those cold, windswept landscapes, were equally impressive, equally bizarre, and equally well adapted to the challenges of their time. Tonight, let us look beyond the shadow of the mammoth and meet one of its most formidable and perhaps slightly less celebrated contemporaries: the woolly rhinoceros, Coelodonta antiquitatis. Imagine a creature built like a furry prehistoric tank, standing perhaps 6 feet tall at the shoulder, significantly larger than most modern rhinos, and weighing several tons. The woolly rhino was a powerhouse of the Pleistocene plains. Its body was low-slung, immensely stocky, covered in a thick, dense coat of reddish-brown or dark fur, providing essential insulation against the bitter cold. Beneath the fur, a thick layer of subcutaneous fat offered further protection. Its most striking feature, however, was its head. It possessed not one, but 2 massive horns rising from its snout. Unlike the horns of cattle, these were not bony cores covered in keratin. They were made entirely of densely packed, matted hair-like fibers, similar in structure to the horns of modern rhinos. The front horn, rising from the tip of its nose, was particularly immense, often flattened side to side like a great curved paddle or scimitar, and could reach lengths of over 3 feet, or 1 meter. A smaller secondary horn sat further back between its eyes. What was the purpose of this incredible headgear? The massive front horn likely served multiple functions. It would have been a formidable defensive weapon against predators like cave lions or dire wolves. We can easily picture the rhino lowering its great head, that immense flattened horn presented as an impenetrable shield or a terrifying battering ram. But perhaps its primary use was related to feeding. Living in a world frequently covered by snow, The woolly rhino needed a way to access the frozen grasses and sedges buried beneath. That broad, flattened horn may have acted as a perfect built-in snowplow, used to sweep aside deep drifts and expose the vegetation below. Imagine it rhythmically swinging its great head from side to side, clearing patches of ground, its powerful neck muscles straining against the snow's resistance. Its teeth confirm its diet. High-crowned complex molars, perfectly adapted for grinding the tough, abrasive grasses and herbs of the mammoth steppe, mark it as a dedicated grazer. Unlike the mammoths, which might have browsed on dwarf willows as well, the woolly rhino seems to have been a specialist of the open grasslands. Its senses were likely well adapted to its environment. Its small eyes suggest relatively poor eyesight, perhaps not crucial in the wide-open landscapes it inhabited. But its large nasal passages hint at a keen sense of smell, vital for detecting predators or locating patches of vegetation hidden beneath the snow. Its prominent ears suggest good hearing as well. Unlike the often vast herds of mammoths, woolly rhinos were likely more solitary creatures, or perhaps lived in small family groups, much like their modern relatives. They were the grumpy, heavily armored loners of the Ice Age plains. Fossils of the woolly rhinoceros, including remarkably preserved frozen carcasses found in the Siberian permafrost, complete with fur, horns, and even stomach contents, paint a vivid picture of a creature perfectly, beautifully adapted to the harsh realities of the glacial world. It was not merely a supporting player, it was a co-star, a magnificent and successful giant in its own right, embodying the rugged, resilient spirit of the Ice Age. And it was far from the only giant sharing the darkness of the Pleistocene nights. Other, even more formidable shadows lurked in the caves and hunted across the frozen plains. While the woolly rhino carved its solitary path across the frozen steppes, other giants sought refuge and perhaps found dominion in different corners of the Ice Age world. The caves and rocky shelters that pockmarked the landscapes of Pleistocene Europe and Asia became the dens, the fortresses, and sometimes the final resting places for two other formidable members of the megafauna: the cave bear, Ursus spelaeus, and the cave lion, Panthera spelaea. Let us first venture into the deep, echoing darkness of a large limestone cave system somewhere in Ice Age Europe. The air here is cold, still, and heavy with the damp scent of mineral rock and perhaps the faint, musky odor of animal occupation. Deep within these subterranean labyrinths, hibernating through the brutal winter months or perhaps seeking shelter year-round, resided the cave bear. This was not simply a brown bear that happened to live in caves. It was a distinct species, and it was immense. Significantly larger than most modern brown bears or grizzlies, a large male cave bear standing on its hind legs might have towered over 10 feet tall, weighing perhaps up to a ton. Its skull was massive, broad, with a distinctively steep forehead, giving it a unique profile. Despite its fearsome size, evidence from its teeth, heavily worn molars, and isotopic analysis of its bones suggests that the cave bear was likely primarily herbivorous or perhaps omnivorous with a strong preference for plants. Imagine it in the summer months, browsing on vegetation, berries, and roots in the woodlands outside its cave system. Its great size might have been less about predation and more about surviving the long, lean winter through sheer bulk and fat reserves, and perhaps defending itself or its hibernation den from predators. Caves were clearly central to its existence. Thousands upon thousands of cave bear bones have been found piled deep within European cave systems, accumulations built up over countless generations seeking shelter within the same ancestral dens. These bone beds paint a picture of a creature intimately tied to these dark, subterranean refugees. They also hint at a high mortality rate, perhaps during hibernation, or maybe due to conflict with another cave dweller. early humans who competed for these same prime shelters. Emerging perhaps from those same caves or stalking the open steppes under the cold moonlight was another very different kind of giant, the cave lion. Again, the name is slightly misleading. It was not necessarily confined to caves, though its remains are often found there, perhaps dragged in by hyenas or sought as shelter. And it was not directly ancestral to modern African lions, but rather a distinct cold-adapted Eurasian lineage, perhaps more closely related to modern tigers. But it was undeniably lion-like and undeniably huge, significantly larger than any lion alive today, perhaps 25% bigger. The cave lion was one of the most powerful terrestrial predators of the Pleistocene. Imagine a lion built on the scale of a Siberian tiger, but adapted for life on the cold, open plains. Its coat was likely thick, perhaps paler and less maned than modern lions, offering camouflage against the snow-dusted landscapes. Cave paintings, left behind by our Ice Age ancestors in places like Chauvet Cave in France, offer hauntingly realistic depictions of these magnificent predators. They are shown as sleek, powerful hunters, often in groups, perhaps suggesting pack hunting behavior similar to modern lions. What did they hunt? Their primary prey was likely the abundant herbivores of the mammoth steppe: horses, reindeer, bison, perhaps even young mammoths or rhinos. They were the apex predators of their time and place, rivaled perhaps only by the great dire wolf packs or the short-faced bears in other regions. The presence of these two giants, the massive, largely herbivorous cave bear dominating the subterranean realm, and the huge, powerful cave lion ruling the nocturnal hunt above, adds another layer of awe and perhaps quiet menace to the Ice Age night. They were creatures perfectly adapted to the cold, lords of their respective domains, embodying the raw power and savage beauty of this frozen world. Their eventual disappearance towards the end of the Pleistocene remains part of the larger megafaunal extinction mystery, leaving behind only their impressive bones in the cold earth and their haunting images painted on the silent walls of ancient caves. And amidst these bears and lions, another creature, perhaps the most elegant giant of all, graced the open landscapes. While the woolly rhino embodied rugged endurance and the cave lion represented predatory power, the Ice Age landscapes were also graced by a creature of breathtaking elegance and astonishing scale. Roaming the open woodlands and steppe tundra margins, particularly across Europe and Asia, was the giant deer, Megaloceros giganteus, often, though somewhat inaccurately, called the Irish elk. This was arguably the largest deer species that has ever lived, standing nearly 7 feet, or over 2 meters, tall at the shoulder, taller than a modern moose. Megaloceros was a truly magnificent herbivore. Its body was powerfully built, yet possessed a certain grace, supported by long, slender legs, suggesting it was capable of considerable speed when necessary. But its defining feature, the characteristic that instantly captures the imagination and sets it apart, was its antlers. Wielded only by the males, these were the largest antlers known from any deer, living or extinct. Imagine a colossal, flattened, palmated rack stretching up to 12 feet or 3.5 meters across from tip to tip and weighing perhaps up to 90 pounds or 40 kilograms. These were not simple spikes or branches. They were vast, intricate, bony structures like immense sculpted fans held aloft on the deer's head. To picture a large male Megaloceros moving through the Ice Age landscape, its head held high, bearing this incredible crown, is to conjure an image of almost mythical grandeur. What was the purpose of such an extravagant and undoubtedly cumbersome biological ornament? Like the elaborate antlers of modern deer, they were almost certainly secondary sexual characteristics, used primarily by males in ritualistic displays and combat to establish dominance and win access to females during the mating season. One can picture two massive stags facing off across a frosty clearing, their immense antlers clashing with a sound that would echo through the quiet woodland, a dramatic, dangerous ballet for the right to reproduce. The sheer size and complexity of the antlers likely served as an honest signal of the male's health, strength, and genetic quality. Only a truly fit individual could afford the immense metabolic cost of growing, carrying, and potentially fighting with such a massive structure. But the antlers may have posed challenges too. Navigating dense forests with a 12-foot wide rack of bone would have been difficult. This might explain why Megaloceros seems to have preferred more open habitats, the park-like woodlands, grasslands, and tundra edges, where movement was less restricted. What did this elegant giant eat? Its teeth, similar to those of modern deer like elk or red deer, suggest it was primarily a browser and grazer, feeding on a mixed diet of grasses, herbs, and the leaves and twigs of shrubs and trees like willow and birch found in its preferred habitats. It was a creature adapted to the specific vegetation mosaic of the Ice Age, capable of exploiting different food sources depending on the season and location. Fossils of Megaloceros, including complete skeletons remarkably preserved in Irish peat bogs, hence the common name Irish elk, though it was neither exclusively Irish nor an elk, give us a clear picture of this magnificent creature. Cave paintings created by early humans also depict it with accuracy and reverence, suggesting it was a familiar and perhaps important part of their world, maybe as a source of food, hides, and awe-inspiring antlers. The giant deer was a symbol of the richness and scale of the Ice Age megafauna. It represented a different kind of success, not just brute force or predatory prowess, but a combination of size, grace, and spectacular ornamentation. Its eventual extinction, occurring relatively late, perhaps only around 7,700 years ago in Siberia, might have been linked to the rapid climate changes at the end of the Ice Age, the disappearance of its preferred open woodland habitats, and perhaps hunting pressure from expanding human populations. Its memory lingers, a ghost of immense antlers against a cold sky, reminding us that the Ice Age was not just a world of shaggy, lumbering brutes, but also a realm of profound and sometimes extravagant beauty. And this beauty took even stranger forms on the isolated continents further south. While the woolly mammoths, rhinos, and giant deer dominated the familiar landscapes of Ice Age Eurasia and North America's mammoth steppe, the story of the Pleistocene megafauna took a different and arguably even stranger turn further south, particularly in the Americas. Here, evolving in relative isolation for millions of years before the Great Land Bridge reconnected North and South America, unique lineages of mammals produced giants of truly bizarre and wonderful forms. Let us meet two of the most iconic representatives of this distinct American Ice Age fauna, the giant ground sloths and the glyptodonts. First, imagine a creature that defies easy categorization. It moves with a slow, ponderous, almost reptilian gait, its immense weight supported by stout, pillar-like legs ending in huge, inwardly curved claws. Its body is massive, perhaps reaching the size of a modern elephant, covered maybe in thick, shaggy fur. Its head seems disproportionately small, with simple, peg-like teeth. This is Megatherium americanum, the largest of the giant ground sloths, a true behemoth of the South American plains and woodlands. These were not the small, slow-moving tree dwellers we know today. The ground sloths of the Ice Age were a diverse group, ranging from pony-sized browsers to these elephantine giants. Megatherium, standing perhaps 12 feet tall when rearing up on its hind legs, was likely a powerful herbivore. Using its immense size and strength, supported perhaps by a thick, tripod-like tail, it could have easily reached high into trees, pulling down entire branches with its long, powerfully clawed forelimbs to strip them of leaves. Those enormous claws might also have been used for digging up roots, or perhaps even as formidable defensive weapons against the predators of its time, like the saber-toothed cat Smilodon. Fossilized skin impressions even reveal that some ground sloths had small, bony plates, osteoderms, embedded within their skin, providing an extra layer of armor. They were slow, perhaps, but they were immensely powerful and well defended. Now, picture another creature sharing these same landscapes, an animal that looks like it lumbered straight out of a fantasy novel. Imagine a mammal built like a Volkswagen Beetle, encased in a solid, domed shell composed of hundreds of fused bony plates. 4 short, sturdy legs carry this armored dome, and a thick, often clubbed or spiked tail trails behind. This is a glyptodont, perhaps a Duodecurus or glyptodon itself. These were giant relatives of modern armadillos, but scaled up to absurd proportions. The largest glyptodonts could weigh over a ton, their rigid, turtle-like shells providing near-impenetrable protection against predators. Unlike a turtle, they could not retract their heads into their shells, but the top of their skull often possessed its own bony cap, completing the suit of armor. Their teeth were simple pegs, adapted for grinding tough grasses and vegetation found in the open pampas and savannas of South America, and later North America after the continents connected. And some species, like Duodecurus, wielded a truly fearsome weapon, a massive spiked tail club, reminiscent perhaps of an ankylosaur dinosaur. This bony mace, swung by powerful tail muscles, would have been a devastating deterrent against any predator brave enough or foolish enough to attack this walking fortress. These two creatures, the elephant-sized, clawed sloth and the car-sized, armored glyptodont, represent just a glimpse into the unique and often bizarre megafauna that evolved in the Americas during the Ice Age. They shared their world with other strange beasts, giant short-faced bears, American lions and cheetahs, unrelated to modern ones, native horses and camels, which later went extinct there, and saber-toothed cats. This distinct American fauna highlights the importance of geography and isolation in shaping the course of evolution. While sharing some similarities with the Eurasian megafauna, the Americas fostered their own unique dynasties, producing giants that followed different evolutionary paths, solving the challenges of Ice Age survival with their own remarkable and sometimes truly weird adaptations. Their presence paints a richer, more complex picture of the Pleistocene world, a planet teeming not just with mammoths, but with a whole bestiary of incredible, forgotten giants. And all these giants, wherever they lived, faced the same fundamental challenge: surviving the cold. How did they do it? How did these magnificent giants, the woolly mammoths, the hulking rhinos, the colossal sloths, the armored glyptodonts, not just survive, but thrive in a world defined by profound, pervasive cold? The Ice Age was not a gentle place. Surviving its long winters, its biting winds, and its frozen landscapes required a suite of sophisticated adaptations, biological solutions honed over millennia to combat the relentless theft of body heat. The most obvious, and perhaps most iconic defense, was insulation. Creatures living in the coldest regions, like the woolly mammoths and rhinos, developed incredibly thick, dense coats of fur. Imagine the mammoth's coat, a complex, multi-layered system. Closest to the skin was a dense, fine undercoat, perhaps several inches thick, trapping a layer of insulating air like the down feathers of an Arctic bird. Overlying this was a much longer, coarser layer of guard hairs, sometimes reaching over 3 feet long, forming a shaggy, protective curtain that shed snow and blocked the wind. This natural parka provided exceptional protection against even the most extreme temperatures. Fossilized carcasses preserved in the Siberian permafrost show just how effective this insulation was, revealing coats of astonishing thickness and complexity. Beneath the fur, another layer of insulation was crucial: fat. A thick layer of subcutaneous blubber, similar perhaps to that found in modern whales or seals, would have provided an essential energy reserve and an additional barrier against heat loss. This was particularly important during the long, lean winters when food was scarce. The animal essentially carried its own internal fuel tank and radiator insulation. Size itself was an adaptation. The sheer bulk of creatures like mammoths, rhinos, and giant sloths worked in their favor according to a simple physical principle known as Bergmann's rule. Larger animals have a smaller surface area relative to their volume compared to smaller animals. This means they lose heat more slowly. Being big was, in itself, a way to stay warm, a strategy of thermal inertia. But adaptation wasn't just about enduring the cold, it was also about finding food in a frozen world. We've already mentioned the woolly rhino's potential snowplow horn. Mammoths likely used their immense curved tusks for similar purposes, sweeping aside snow to uncover buried grasses and sedges. Their high-crowned, ridged molars were perfect grinding machines for processing the tough, abrasive, cold-adapted vegetation of the steppe. And when local conditions became too harsh, when food became too scarce, many of these giants employed another crucial survival strategy: migration. Vast herds of mammoths, bison, horses, and reindeer likely undertook immense seasonal journeys across the mammoth steppe, following the shifting patterns of vegetation growth, moving between summer and winter feeding grounds, sometimes covering thousands of miles. Their long legs and efficient locomotion were adaptations not just for escaping predators, but for traversing the immense, open landscapes of their world in search of sustenance. Even creatures that didn't undertake long migrations likely adapted their behavior, seeking shelter from the wind in valleys or behind natural rock formations, reducing activity levels during the coldest periods to conserve energy, perhaps entering states of torpor or even hibernation, as the cave bears undoubtedly did. Survival in the Ice Age was a complex equation, solved through a combination of anatomical, physiological, and behavioral adaptations. It required thick fur, insulating fat, large size, specialized feeding tools, and often the ability to move vast distances. These giants were not simply clumsy brutes enduring the cold, they were highly specialized, exquisitely adapted masters of their frozen kingdom. And the sheer scale of their success was evident in the vast herds that populated the Pleistocene world, their presence shaping the very soundscape of the age. While the Ice Age night held the sharp cries of predators and the eerie groans of shifting ice, the days, and perhaps even the calmer nights across the vast expanse of the mammoth steppe would have carried a different kind of sound, a deep, resonant, and almost geological rumble. This was the sound of the great herds, the sheer collective presence of the megafauna that defined this age. Imagine yourself standing on a low rise, looking out across the immense, wind-swept plain of Beringia, or the grasslands bordering the European ice sheets. In the distance, perhaps miles away, you see them, not as individuals, but as a vast, dark, slowly moving river of life. A herd of woolly mammoths, numbering perhaps in the hundreds or even thousands. From this distance you hear not individual footsteps, but a low, continuous thrumming, a vibration that travels through the frozen ground as much as through the air. It is the collective rhythm of thousands of immense pillar-like legs pressing down on the permafrost, a sound less like walking and more like a slow, distant earthquake. Interspersed with this deep, foundational rumble might be the sounds of the herd itself, carried faintly on the cold, dry wind. The occasional deep, resonant trumpet call of a matriarch communicating across the vastness. The lower, rumbling growls and grunts of males interacting. The higher-pitched calls of young mammoths staying close to their mothers. It is not a loud cacophony, but a complex, low-frequency conversation. The social fabric of the herd made audible. Or perhaps the herd you see is not mammoths, but steppe bison, Bison priscus, larger, shaggier, and perhaps more numerous than their modern descendants. Their passage might be marked by a more rapid drumming of hooves, a higher-pitched sound than the mammoth's tread, accompanied by the occasional bellow or the sharp clash of horns as young males test their strength. Further off maybe, a flash of movement. A herd of wild Ice Age horses, their coats perhaps dun-coloured or striped for camouflage against the steppe grasses, galloping across the plain, their hoofbeats a faster, lighter rhythm against the deep bass note of the larger giants. These sounds, heard from afar, are not necessarily threatening. They are awe-inspiring. They speak of the sheer scale and abundance of life that this seemingly barren, frozen world could support. They paint a picture of an ecosystem operating at a different level of magnitude, a world where creatures weighing many tons were not rare exceptions, but the common landscape-shaping norm. The presence of these great herds would have been palpable even when unseen. The air might carry their scent for miles, a heavy, musky animal smell. The ground itself would bear the marks of their passage. Vast networks of trails trampled into the permafrost, areas of vegetation heavily grazed, perhaps even trees rubbed smooth or pushed over by the immense bodies. To witness, even in imagination, the slow, majestic passage of a great mammoth herd across the vast, silent landscape of the Ice Age is to glimpse the true heart of this forgotten world. It was not just a world of ice and cold. It was a world of colossal life. A kingdom of giants whose deep, resonant presence echoed across the frozen plains. But this kingdom, like all the forgotten worlds before it, was living on borrowed time. The great cycles of the earth were turning once more, and a profound change was coming, one that would silence the thunder of the herds forever. The peak of the last glacial maximum, that period of profound cold and immense ice sheets, could not last forever. The same celestial metronome, the Milankovitch cycles, that had nudged the planet into its deep freeze eventually shifted their alignment. Slowly, subtly, the distribution of sunlight began to change once more. Northern Hemisphere summers started receiving slightly more solar energy. The balance tipped. The long winter began its slow, inexorable retreat. The great melt had begun. This was not a sudden, overnight event. It was a process that unfolded over thousands of years, beginning perhaps around 20,000 years ago, and accelerating significantly after about 15,000 years ago. But on a geological timescale, it was a dramatic and transformative thaw. Imagine the colossal Laurentide and Fennoscandian ice sheets, those miles-thick behemoths that had dominated the continents. Warmed from above by the strengthening summer sun, and perhaps lubricated from below by meltwater seeping down to the bedrock, they began to stagnate, their outward flow slowing. Then their edges, particularly their southern margins, began to retreat. This retreat was not a smooth, uniform melting back. It was likely a complex, messy affair. Great lobes of the ice sheet might have surged forward temporarily, only to collapse back later. Vast sections might have become detached, forming stagnant, isolated blocks of dead ice that would take centuries, even millennia, to melt completely. The sheer volume of meltwater produced was staggering. During the peak melting periods, immense rivers, far larger than any rivers on Earth today, would have gushed from beneath the receding ice margins. These torrents, choked with the glacial flour and rocky debris carried by the ice, carved new valleys and deposited vast plains of sand and gravel. Where the retreating ice blocked the natural drainage routes, colossal proglacial lakes formed, dammed by the ice itself. Lake Agassiz in central North America was perhaps the largest freshwater lake that has ever existed, larger than all the modern Great Lakes combined, holding meltwater from the Laurentide sheet. Periodically, the ice dams holding back these immense lakes would fail catastrophically. Imagine a wall of ice hundreds of feet high suddenly giving way. The resulting megafloods would have been events of unimaginable violence, scouring landscapes down to bedrock in a matter of days, carving features like the channeled scablands of Washington state. The landscape left behind by the retreating ice was raw, scarred, and utterly transformed. Vast tracts of land, scraped bare down to the bedrock, were littered with moraines, jumbled ridges of boulders, gravel and sand dropped by the melting ice. Strange elongated hills called drumlins recorded the direction of the ice flow. Winding ridges of sand and gravel called eskers marked the courses of rivers that had flowed within or beneath the ice itself. Countless hollows, carved by the ice or left by melting blocks of stagnant ice, filled with water, creating the tens of thousands of lakes that dot landscapes like Canada, Minnesota, and Scandinavia today. This was a world being actively, dramatically reshaped by the death throes of the ice monsters. It was a landscape of immense floods, shifting rivers, forming lakes, and raw, newly exposed rock. The Great Melt was not just a warming, it was a fundamental replumbing and resculpting of the planet's surface. The ice, which had dominated for so long, was relinquishing its grip, but in its retreat, it left behind an unmistakable, enduring signature etched into the very bones of the continents. And as the water locked away and the ice returned to the liquid world, it triggered another, equally profound global transformation. The oceans began to rise. The colossal ice sheets were melting, releasing their hold on the continents and pouring unimaginable volumes of fresh water back into the global ocean. The great planetary theft of water, which had defined the glacial maximum, was now being reversed. The oceans, which had retreated nearly 400 feet, began their slow, relentless, and inevitable rise. This was not a sudden catastrophic flood across the globe, though localized megafloods from melting glaciers were certainly occurring. It was a gradual, yet geologically swift inundation, playing out over thousands of years as the meltwater returned to the sea. Imagine the global sea level rising, inch by inch, foot by foot, decade after decade, century after century. The most immediate and dramatic consequence of this rise was the drowning of those vast, low-lying landscapes that had been exposed during the glacial maximum, the continental shelves, and, crucially, the great land bridges. Let us return first to Beringia, that immense subcontinent connecting Asia and North America. As the ice melted and sea levels rose, the waters of the Arctic and Pacific Oceans began to creep inwards from the north and south. What was once a vast, continuous plain of mammoth steppe became increasingly fragmented. Coastlines retreated, river valleys flooded, becoming shallow estuaries, low-lying areas transformed into vast marshes. Imagine the perspective of the animals, the mammoths, bison, horses, and the early humans who inhabited this land. Their world was shrinking. Migration routes that had existed for millennia were slowly being severed by the encroaching water. Populations became isolated. The vast open highway was closing. Sometime around 11,000 years ago, the final connection was likely broken. The waters met. The Bering Strait was reformed, perhaps initially as a shallow, narrow channel, but gradually widening and deepening into the seaway we know today. An entire subcontinent, a unique ecosystem that had persisted for tens of thousands of years, vanished beneath the waves, taking its secrets with it, leaving only scattered fossils on the seabed and isolated populations on either side of the newly formed strait. A similar, perhaps even more poignant drama unfolded in Doggerland, that lost heartland of Europe beneath the North Sea. Here too, the rising waters relentlessly reclaimed the land. What had been rolling hills became islands. What had been river valleys became deep fjords or shallow bays. The vast plain, home to Mesolithic hunters and abundant game, shrank year by year. Imagine the human perspective. Generations of people who had lived, hunted, and perhaps even built settlements in this rich landscape found their territories shrinking, their familiar hunting grounds disappearing beneath the rising tide. Oral histories, passed down through millennia, might hold faint echoes of this time. Myths of sunken lands, of great floods, of a world lost to the sea. The final submergence of Doggerland was likely a complex process, perhaps accelerated by sudden events like the Storegga Slide tsunami. By about 6,500 BC, Doggerland, as a contiguous landmass, was gone, replaced by the shallow, turbulent waters of the North Sea. A human world, a rich ecosystem, drowned and forgotten, its memory preserved only in the artifacts occasionally dredged up by fishermen. This global rise in sea level, driven by the melting ice, was one of the most profound transformations of the post-glacial world. It redrew the coastlines of every continent. It created islands where there were once hills. It severed connections that had shaped the course of life and human migration for millennia. The forgotten oceans of the Ice Age weren't just the cold, altered seas that persisted throughout the glacial period. They were also these vast, temporarily revealed landscapes, these drowned worlds like Beringia and Doggerland. Their story is a powerful reminder that the map of our planet is fluid, that land can become sea, and sea can become land, driven by the great, slow cycles of planetary climate. The water had returned, reclaiming its domain and bringing an end to the unique geographical configuration of the Ice Age world. But as the waters rose, the giants who had defined that world were facing their own final crisis. The ice was retreating, the seas were rising, the world was warming, transforming rapidly from the frozen landscapes of the glacial maximum into something closer, though not identical, to the world we know today. But this great thaw, this apparent return to a more hospitable climate, coincided with another far more tragic event: the disappearance of the giants. Across the globe, as the Pleistocene epoch gave way to the Holocene, our current epoch, around 11,700 years ago, the magnificent megafauna that had defined the Ice Age began to vanish. The woolly mammoths, the woolly rhinoceroses, the cave lions, the cave bears, the giant deer, the colossal ground sloths, the armored glyptodonts, the saber-toothed cats, the dire wolves, the native horses and camels of the Americas, an entire bestiary of incredible creatures, large and small, disappeared from the face of the Earth in a relatively short geological window. This quaternary megafauna extinction was not as instantaneous or as globally comprehensive as the Great Dying at the end of the Permian. It was more staggered, affecting different continents and different species at slightly different times, often concentrated around the end of the last glacial period. But it was nonetheless a profound biological crisis, fundamentally reshaping the planet's ecosystems. Why? Why did these creatures, which had successfully endured the extreme cold and harsh conditions of multiple glacial cycles, suddenly vanish during the warming phase, the very period that should, intuitively, have offered relief? This question remains one of the most intensely debated mysteries in paleontology, a complex puzzle with two primary and perhaps intertwining suspects. The first suspect is climate change itself. The end of the Ice Age was not a gentle, gradual warming. It was a period of rapid, sometimes chaotic, climatic shifts. Temperatures rose significantly, yes, but perhaps more importantly, precipitation patterns changed dramatically. The vast, cool, dry mammoth steppe ecosystem, which had provided the primary food source for so many of the great grazers, began to shrink and fragment, replaced by expanding forests in some areas, boggier tundra in others, and different types of grasslands elsewhere. This habitat change could have been devastating for animals highly specialized to the unique vegetation and conditions of the steppe. Imagine the woolly mammoths adapted to eat dry grasses and forbs, struggling to find sustenance in newly spreading, wetter forests or less nutritious tundra. their world was vanishing, not under ice, but under ecological transformation. The second major suspect is us. This period of rapid warming and megafaunal decline coincided precisely with the global expansion and technological advancement of modern humans, Homo sapiens. Armed with increasingly sophisticated hunting tools, like Clovis points in North America, cooperative hunting strategies, and perhaps the use of fire to manage landscapes, humans were becoming incredibly effective predators. The overkill hypothesis suggests that these newly arrived or newly empowered human hunters, encountering megafauna that had perhaps never faced such an intelligent and adaptable predator before, simply hunted them to extinction. The giants, with their slow reproductive rates, would have been particularly vulnerable to sustained hunting pressure, especially when already stressed by the rapidly changing environment. Imagine small bands of human hunters working together, capable of bringing down even the largest mammoths or bison. Could they have tipped the balance towards extinction? Was it the climate changing their world too fast, or was it the arrival of a new, uniquely lethal predator? The debate continues fiercely. Proponents of the climate change hypothesis point to previous extinction pulses associated with earlier warming periods before humans were a significant factor. They argue that the sheer scale of the habitat transformation was the primary driver. Proponents of the overkill hypothesis point to the striking temporal correlation between human arrival in new continents, like the Americas and Australia, and the rapid disappearance of the megafauna there. They argue that climate change alone cannot explain the pattern and timing of the extinctions. Increasingly, many scientists believe the answer is likely not one or the other, but a synergistic combination of both. Perhaps climate change stressed the megafauna populations, shrinking their habitats, reducing their numbers, making them more vulnerable. And then, human hunting pressure provided the final decisive blow, pushing already struggling species over the brink. Whatever the precise cause or combination of causes, the result was the same. The giants vanished. The world was suddenly, profoundly emptier. The thundering herds fell silent, and the planet entered a new phase, an era dominated not by colossal beasts, but by smaller, more adaptable creatures, and increasingly by the single, highly intelligent primate species that had perhaps played a role in the giants' demise. The Ice Age was over, and its most iconic inhabitants were gone, leaving behind only their bones, their tusks, and the enduring landscapes they had once roamed. The great ice sheets have retreated, the giants have fallen silent, and the world has settled into the warmer embrace of our current interglacial period, the Holocene. But the Ice Age, though technically over, did not simply vanish without a trace. Its passage, particularly the immense power of those continental glaciers, left behind a profound and enduring physical legacy, scars etched deeply into the very surface of the Earth, shaping the landscapes we inhabit today in ways we often fail to recognize. Imagine traveling across the northern parts of North America or Europe, regions once buried beneath miles of Laurentide or Fennoscandian ice. The evidence of the glacier's passage is everywhere, written in the very shape of the land. Look at the hills. Many are low, elongated, teardrop-shaped mounds, often occurring in vast swarms, all aligned in the same direction. These are drumlins, sculpted by the flowing ice at the base of the glacier, their streamlined forms recording the direction of the ancient ice flow like giant, earthen weather vanes. Look at the valleys carved through mountainous regions. They are not the sharp, V-shaped valleys typically carved by rivers. They are broad, flat-bottomed, steep-sided, U-shaped valleys, their distinctive profile scoured out by the immense erosive power of valley glaciers grinding their way down from the highlands. High on the valley walls, smaller hanging valleys might mark the entry points of tributary glaciers that once fed the main ice flow. Look at the coastlines, particularly in places like Norway, Alaska, or New Zealand. Deep, dramatic fjords, long, narrow inlets of the sea with steep cliffs, penetrate far inland. These are glacial valleys that were carved below the sea level of their time, drowned by the rising waters as the ice melted. Their breathtaking beauty is a direct consequence of glacial erosion. Look at the lakes. Tens of thousands, perhaps millions of lakes, large and small, dot the landscapes once covered by ice. Many fill depressions scoured out by the moving ice itself. Others occupy kettle holes, formed when large, isolated blocks of stagnant ice, left behind by the retreating glacier, were buried in sediment and then slowly melted, leaving behind water-filled pits. The Great Lakes of North America themselves owe their existence, in large part, to the scouring and damming action of the Laurentide ice sheet. Look at the soil and the rocks. Vast areas are covered by glacial till, an unsorted jumble of clay, sand, gravel, and boulders, picked up, transported, sometimes for hundreds of miles, and then simply dropped by the melting ice. Long, winding ridges called moraines mark the former edges or pauses in the retreat of the ice sheet, ridges composed entirely of this glacial debris. Strange, sinuous ridges of sand and gravel called eskers snake across the landscape, marking the courses of meltwater rivers that flowed within or beneath the ice itself. And scattered randomly across the land, sometimes perched precariously on hilltops, are erratics, massive boulders, compositionally different from the local bedrock, carried far from their origin and deposited gently by the melting ice, like geological calling cards left by the vanished giants. Even the drainage patterns of entire continents were reshaped. Rivers were diverted, forced into new courses by the advancing ice or the newly formed glacial landforms. Great lakes formed and drained, carving new outlets. The modern courses of rivers like the Missouri and the Ohio in North America bear the unmistakable signature of diversions caused by the Laurentide ice sheet. This glacial fingerprint is not subtle. It is written large across vast swathes of our planet. The very shape of the ground we walk on, the lakes we swim in, the valleys we admire, the soil we farm, much of it is a direct inheritance from the last great advance and retreat of the ice. The Ice Age may be over, but its physical presence endures. The land itself remembers the crushing weight, the scouring power, the transformative presence of the great ice sheets. These landforms are the silent, enduring monuments to a time when ice ruled the world, a geological legacy that continues to shape our landscapes, our ecosystems, and even our lives, tens of thousands of years after the Great Melt began. And the legacy wasn't just physical, it was biological too, seeding the land for future growth. The retreat of the great ice sheets left behind a landscape dramatically reshaped, scoured valleys, newly formed lakes, and rearranged river systems. But the glaciers bequeathed another, perhaps even more significant legacy, one hidden not in the grand shapes of the land, but within the very substance of the ground itself. As the ice melted, it deposited immense quantities of fine-grained, mineral-rich sediment, creating some of the most fertile soils on the planet, foundations upon which future ecosystems and eventually human agriculture would thrive. Remember the immense erosive power of those miles-thick glaciers. As they flowed across the continents, they acted like colossal sheets of sandpaper, grinding the underlying bedrock, granite, limestone, shale, whatever lay beneath, into a fine powder. This glacial flour, composed of freshly pulverized, unweathered rock particles, was incredibly rich in the essential minerals needed for plant growth: phosphorus, potassium, calcium, magnesium. Vast quantities of this mineral-rich powder were transported, frozen within the ice, or carried along by meltwater streams flowing beneath the glaciers. When the ice finally melted, This material was deposited across the landscape in several ways. Directly beneath the ice, glacial till was laid down, that unsorted mixture of clay, silt, sand, gravel, and boulders. While till itself can be dense and difficult to farm directly, its slow weathering over time releases those essential minerals into the surrounding environment. More significantly, the meltwater rivers pouring out from the receding ice carried immense loads of that fine glacial flour. As these rivers slowed down upon reaching flatter ground or proglacial lakes, they deposited this fine silt, creating vast, flat outwash plains and lakebed sediments. These deposits were naturally sorted by the water, resulting in deep, stone-free, mineral-rich soils perfect for future plant colonization. And perhaps most importantly, there was the wind. Remember those immense dust storms that characterized the Ice Age atmosphere? They were picking up not just any dust, but primarily that fine, mineral-rich glacial flour from the outwash plains and barren grounds near the ice margins. This wind-blown silt, known as loess, was carried for hundreds, even thousands of miles, blanketing vast regions downwind of the ice sheets in thick, fertile layers. Regions like the American Midwest, the Pampas of Argentina, large parts of Central Europe, and the Yellow River Basin in China owe their incredible agricultural productivity today, in large part, to these deep, ancient deposits of loess laid down during the Ice Age. It was a planetary-scale delivery of fresh, potent fertilizer, courtesy of the grinding glaciers and the relentless wind. Imagine the world just after the ice retreated. The raw, scoured landscapes were initially barren, but the newly deposited till, the outwash sediments, and the blankets of loess provided a perfect seedbed. As the climate warmed, pioneer plants, hardy grasses, herbs, shrubs, and eventually trees, began to colonize these fresh, mineral-rich substrates. They found a ground primed for growth, bursting with the essential nutrients unlocked from the bedrock by the ice. This rapid colonization of the post-glacial landscapes helped to stabilize the loose sediments, preventing further erosion, and began the slow process of building new, complex ecosystems. The forests returned, the grasslands expanded, and life rebounded with vigor, fueled in part by this geological gift from the vanished ice. This legacy of fertile soil is one of the most profound yet often overlooked consequences of the Ice Age. The glaciers were agents of immense destruction, yes, scraping landscapes bare, but they were also agents of creation, grinding down ancient rocks and redistributing their essential minerals across vast areas, rejuvenating the land and laying the groundwork for the fertile plains that would eventually support vast herds of animals, dense forests, and ultimately the rise of human agriculture and civilization. The very bread we eat has its deepest roots in the dust of the Ice Age, and it was upon these recovering landscapes that our own species truly began its global journey. The ice has retreated, leaving behind a reshaped land and newly fertile soil. The great giants have fallen silent, their reign replaced by the smaller, more familiar fauna of our modern world. The oceans have risen, swallowing the lost land bridges. The earth, scarred but resilient, has settled into the warmer embrace of the Holocene, our current interglacial period. The Ice Age, in its strictest sense, is over. But its echoes, its profound influence, resonate even now, not just in the landscapes around us, but deep within the story of our own species. For humanity, the Ice Age was not a distant, geological curiosity. It was the crucible. It was the harsh, dynamic, and challenging world in which Homo sapiens came of age, migrated across the globe, and developed the ingenuity, adaptability, and social cooperation that define us. Our ancestors lived through these dramatic cycles of cold and warmth. They navigated the shifting landscapes of tundra and steppe. They followed the great herds across the Beringia land bridge into the Americas and perhaps crossed the vanished plains of Doggerland. They sought shelter in caves, painted the images of the giants they lived alongside onto stone walls, and learned to master fire, tools, and clothing to survive the profound cold. The very pressures of the Ice Age environment likely played a crucial role in shaping our own evolution, favoring larger brains capable of complex problem-solving, fostering social bonds necessary for cooperative hunting and survival, and driving technological innovation in the face of relentless environmental challenge. We are, in a very real sense, children of the ice. The end of the last glacial period, the Great Melt, coincided with, and perhaps even enabled, another profound revolution: the dawn of agriculture. As the climate stabilized and the fertile post-glacial soils became available, human populations in various parts of the world began the slow transition from nomadic hunting and gathering to settled farming, laying the groundwork for villages, cities, and the complex civilizations that followed. The very landscapes sculpted by the ice became the cradle of our modern world. And so, our journey through the Ice Age concludes not just with a portrait of a lost world, but with a deeper understanding of our own connection to it. It teaches us about the immense power of climate to shape planetary history, driving glaciations, altering sea levels, and dictating the course of life itself. It reminds us of the cyclical nature of our planet, the long, slow rhythms of warmth and cold, expansion and retreat, that operate on timescales far beyond our everyday perception. It showcases the incredible resilience of life, its ability to adapt, to endure, and to find opportunity even in the harshest of conditions. And it highlights the profound impermanence of the world, the constant, ongoing transformation of landscapes, ecosystems, and the very map of the Earth. Perhaps the next time you feel the chill of a winter wind, you can imagine it sweeping across the vast, treeless expanse of the Mammoth Steppe. Perhaps when you see a great lake carved into the land, you can picture the colossal glacier that sculpted its basin. Perhaps when you look at the stars on a clear, cold night, you can remember that you are seeing them through an atmosphere shaped in part by the breath of Ice Age forests and oceans. The Ice Age is not just a chapter in a history book. It is written into the hills, the lakes, the soil, and even, perhaps, into the deeper layers of our own human consciousness. It is a reminder of the Earth's immense power, its capacity for dramatic change, and the enduring, quiet strength of life navigating the long, slow currents of deep time.